We've got measuring the speed of Red Queen's race with Richard Harong.
Cool, thank you. So yeah, I'm Rich Harong, and the talk today is measuring the speed of the Red Queen's race. So this is co-presented with Felipe Ducau. So I'm Rich Harong. I'm research director at Sophos. I've been working at the intersection of machine learning, security, and privacy for about 8 years now. I'm formerly with the US Army Research Laboratory. Felipe is a principal data scientist at Sophos. He's out of the NYU Center for Data Science, and he's been working with Sophos for about 2 years now on the design and evaluation of deep learning models. The Sophos data science team, this is us, and we're data scientists, researchers, engineers, and our job is basically to squeeze machine learning and data science technology into every Sophos product where it makes sense to do it. So if that sounds like something that's up your alley, you should come talk to me afterwards. So the talk in 3 bullet points here. So as everyone knows, it's almost sort of trite to say it these days, the threat landscape is constantly changing and we constantly have to adapt our detection strategies to keep up with it. But knowing something about how fast and in what ways these threats are changing actually might give us an opportunity to be proactive about it instead of constantly being in this reactive mode, or at least have some ability to, plan ahead into the future and decide how we're going to allocate resources. So what I'm going to try and convince you of today is that machine learning, as well as sort of being a proven technology for detecting malware in the wild, can also be used in an analytic role to get some interesting information out about sort of these questions, how fast and in what way the threat landscape is changing. So important caveats, this is a 25-minute talk. Lots of technical details are on the floor. If you have questions, please talk to me afterwards. I'd love to talk to you about them. Also, Felipe and I are both data scientists, not malware analysts. So if we make mistakes in that domain, please forgive us. And also our conclusions are very machine learning centric. So, measuring the speed of the Red Queen's race, if you're not familiar with the reference, it's from Alice in Wonderland. Alice meets a character called the Red Queen who tells her that just to stay where you are, you've got to run as fast as you possibly can, and if you want to actually get anywhere, you've got to go twice as fast as that. And if you've been working, in the malware realm for any length of time, that's probably a painfully familiar statement, right? So we start back in the 70s and the 80s. We've just got viruses, it's vandalism, it's not a whole lot of sort of intent behind it. Then you move on to rats, loggers, bots, DDoS. You've got more platforms, IoT, mobile, SCADA. You go into crimeware and actually like nation state weapons. So just more and more, faster and faster, and it gets wilder and wilder. And so within this sort of race, we've got 2 major static detection paradigms. So this entire talk is static. I'm not talking about any dynamic analysis here. And basically, sort of broadly speaking, you've got signatures, which are great in that they're incredibly specific. They can be tuned to have a very low false positive rate. But their downside is they don't tend to generalize well to new samples. So if you've got a whole bunch of signatures and someone develops a whole new malware, very often your signatures are not going to pick it up. Machine learning is the application of sort of statistical pattern recognition to this malware detection problem. So this is really good in that it tends to generalize well. So if you have new samples, very often a machine learning model will detect them. The price you pay for that is you often get a higher false positive rate, and so you've got to do some engineering about how to reduce that. So when I say statistical pattern recognition applied to the malware landscape, that probably needs a little more explanation. So I'm going to take a quick digression into a crash primer on deep learning that I hope will help motivate the rest of the talk. So this is a toy problem. This is totally made up data for the purposes of illustration. But let's pretend that we're in sort of a nice happy world where the only 2 numbers I need to know about a file to guess whether it's good or bad is its entropy, which I'm going to plot along the x-axis. And if you're not familiar with that, think of it as a measure of compression or encryption. And then the average length of the printable strings within the file, right? So I have those 2 numbers, and now each dot on this plot is going to be a notional PE file, portable executable. And my green dots are all going to be benign files, my red dots are all going to be malicious files. And what I'd like to do is get from this, where I've just got sort of a scatter of data on my plots, into something where I've got sort of regions defined. So I say, hey, look, all of this good stuff looks like it's sort of out around the corners of this plot. All of the bad stuff looks like it's in the center. So next time I see something that's not one of these dots, but it's in the center, I should be able to call it malware and feel good about it. Okay, so how do we get from these scattered points into these regions? We're going to get there with something called a deep neural network. And they're made to sound a lot more complicated than they really are. Basically, within this diagram, all of these circles are going to be numbers, right? They're either going to be numbers that I put into it, numbers that my model is computing sort of as it's processing the data, or at the far right, it's going to be a number that the model spits out. All of these lines are going to represent weights. They're just going to be single numbers, and these weights define the computation, right? And as you change the weights, the computation that this graph does is going to be different. And so initially, I'm just going to set all of these weights to random numbers. So you put your string length into one node, you put your entropy into the other node, math happens as it propagates through this network, and then out the other end, you'll get a malware score. And so if we want to train this so it actually does something useful, what we'll do is we'll randomly sample our data, put those two numbers in, we get a malware score out, and then we look at the difference between the score our model gave us and the label that we know is actually true because we've got all this labeled data. The first time we do it, the answer is going to be hot garbage because we initialized all of our weights completely randomly. But that's fine. All we're going to do is take that comparison we did and use it to error correct all of those weights. And then we spend a lot of money on GPUs and we just do this a lot. And you just do it, essentially you do this cycle, you sample, you compute, you compare, you tweak over and over and over until you get a good model. And so here it is, your recipe for an amazing machine learning classifier, everything you need to know in one slide. You take your labeled data on the left, you add a model to it, you run a training loop on it, and to the right you get this sort of prediction regions for where goodware and malware live. And you deploy it, you protect all of your customers, you earn millions of dollars, ticker tape parade, everyone celebrates. But if you're sitting in your room, sitting in this room, you know that it's probably never that easy. So remember, our model was trained on data that looked like this. 6 weeks later, we have all of these new clusters of malware that have popped up in these black dots. And our model performance is no longer looking quite so hot, right? So we've got some of the clusters it's doing pretty well on. It's got them mostly correct. A lot of these other clusters, it has significant errors to the point where it's getting them completely wrong. But this is interesting, and this is where I'm trying to convince you that they're a good analytic tool, because the degree to which the model underperforms is the degree to which the malware landscape has changed. If the malware landscape never changed, our models would be great forever, but it does change, and so the more it changes, the more our models sort of fall apart. Okay, so to explore this a little further, I'm going to use a tool called model confidence. And the basic intuition we're going to run with is this. If I have new stuff that's on the borderline, I should feel a little bit uncomfortable about that classification, right? If it's sort of straddling these zones between malicious and benign, then maybe I'm a little bit more uncertain. Then if I zoom way out and I see some new family pop up just way, way, way far away from all of my other data, I should be really skeptical of what it's doing, right? So here my model is telling me, hey, that's fine, but it looks nothing like any of this other data I've ever seen before, so how much do I really trust it? So what we're going to do, and this is where these technical details are being dropped very heavily on the floor. I'll have a citation in a few slides, but basically we sort of wiggle these decision boundaries a little bit, and that's a very precise technical term. And what we do is we ask if these classifications from all of these various decision boundaries that we find agree or disagree on a region. So if I have 10 models and all 10 of them say, hey, yeah, this malicious point is definitely malicious, then I feel pretty good about that, right? And I sort of trust that decision. If I've got 5 of these like tiny models that I fit that say they're fine, and 5 of them that say, oh, it's bad, then at that point I should feel a little less certain about it. So if you plot sort of how much these submodels agree on the data, you end up with something like this, where instead of good and bad, now I'm plotting high confidence and low confidence. And then if you zoom out, we see that it assigns a very low confidence to these points that are very far away. So sort of the intuition to take from this is that high confidence means the model has seen data like this before, and then low confidence means that this data looks sort of new from the perspective of your machine learning model. If you're interested in more details, the link to the paper that we're basing a lot of this on is right there, and it'll be in our white paper as well. Okay, so that was all made-up data. Let's take a look at the historical data that we've got from this, with this tool in mind. So just a caveat, the real data that we're working with is much more complicated. 2 numbers are not enough. We actually use 1,000 numbers to sort of describe each portable executable file. And then the number of nodes in the network goes up as well. Just the main thing to take from the slide as it gets more complicated. So how are we going to use this confidence metric to measure the changes in malware distribution? We're basically going to collect data month over month for all of 2017 and a little bit of 2018, 3 million samples per month. Then we train a model on just the January data. Then we take that model and we evaluate it on the February data, on the March, April, and so forth. And every step we're going to say, how many high confidence samples does the January model find in this month's data, and how many low confidence samples does the January model find in this month's data? And then you do that same process for February, for March, and so on. And you can plot it like this. So on my x-axis here, I've got the number of months post-training, so think of this as how old the model is. And on the y-axis, this is just the number of new low confidence samples that the model is seeing. So you can see the older the model gets, the more low confidence samples appear. So it's a little bit noisy, but there's a pretty clear trend. So that line represents the January model tested on all subsequent months. You add another line for the February model tested on all subsequent months. And then you do it for the rest of the months. And so you can sort of eyeball this, right? There's a pretty good trend in there. And this is the rate of new stuff from the model's perspective that's appearing. And I'm not going to walk through the build, but you can do the same thing for the high confidence samples. Again, each line in this plot represents a separate month where a model has been trained and then tested on all future data. So these are both forms of model decay. This is how much new stuff is appearing that the model doesn't really feel good about classifying, and how much old stuff is vanishing that the model sort of wanted to hang on to because it felt really good about it. And there's noise in there, but there's definitely some very clear trends that pop out. And if you just fit a best fit line, I've disconnected all of the lines. These are just like points that are at the intersections of those lines before. You can see that these low confidence samples rise at a rate of about 1% per quarter. These high confidence samples are falling at a rate of about 4% a quarter. So one of the things you can take away from this is, from the perspective of a machine learning model, the decay is happening much faster as old samples are retired, and there's less change happening as a result of new samples being introduced. Okay, so that was sort of a 50,000-foot overview, like the malware landscape as a whole. How is it changing within a single family? So here, what we're going to do is kind of the same thing. So I've got January training data that's developing, that's producing a January model. And then I'm using 2 samples, or 2 families as a test case for this. I'm using WannaCry just because, it's cool. And Hello World just because we happen to have a lot of it in the data, and it formed a nice test case for this. And we're going to do the same thing. We're taking all of the data from all of, say, 2017 for WannaCry, and we're running it through each of these models individually, and we're counting up the number of high confidence and low confidence samples that we get. And so what we end up with is a plot of confidence over time for high confidence and low confidence samples month over month. So the x-axis here is the month that the model was trained on. The y-axis is going to be a proportion, and I want to call your attention to the log scale here. The blue line is the proportion of high confidence samples. The red line is the proportion of low confidence samples. Horizontal line is when I first see samples from this family appear in the training data. WannaCry came out in sort of first quarter of 2017, so our first samples appear in March. Hello World's a very old one, I think, 2007, 2008. We just happen to not have any samples in January, so it forms sort of a good comparison test case. And what you can see is, if you look at the high confidence region, WannaCry has a very variable high confidence region. It's the proportion of samples that a given model thinks is high confidence drops to as low as 70% after it first appears in the training data. Hello World, it's basically pegged almost at 100% confidence for the entire series of data that we've got. Similar pattern in the low confidence region. So WannaCry has a low confidence proportion that's as high as 9% and never gets down below about 0.2%. So it's a lot more variable. There's a lot more new stuff in there month over month that these models are not really recognizing as something that they've seen before. Hello World, as soon as you see a single sample of it, right, the model says, okay, I've got this pegged. There's nothing new under the sun for me within this family. And one other thing that I kind of want to draw your attention to, this is a little bit of a sidebar, but I think this helps drive home one of the differences between machine learning-based detection and signature-based detection. If you look just at the high confidence for WannaCry, before we have any WannaCry samples in our training data, a machine learning model has enough other points of reference, other forms of malware in that data, that it can actually say, yeah, 56% of these WannaCry samples, even though I have no actual WannaCry samples in my data, I'm willing to say these are high confidence. And in fact, 99.98% of those that are in that high confidence bucket get correctly labeled by the machine learning model as being malicious. So the machine learning models do actually generalize a bit well, and I thought this was a nice validation of the model confidence as well. So, step back a little bit. One of the things that I was talking about before was talking about distances, right? If stuff is really far away from the training data, so why don't we just measure distance in this high-dimensional space? So large distances sort of mean larger changes in these statistical properties. So what we're going to do is we're going to do a month-over-month comparison of samples from the same family. So for example, I'm just, if I've got malware A here in January, and then that's my red dots, I've got malware A in February, that's my black dots, and I'm just going to measure all of these distances between my stuff in February and the nearest sample point in the January data. And I do that for the March data, and I see that these distances are growing, and I do that for the April and for May and so on. And so as this malware family evolves over time, I see these distances change and grow, right? Maybe they grow, maybe they shrink, but there's some variation in that distance that reflects how much this model family, how much this family is changing from the point of view of the machine learning representation of it. And if you look at real data, in fact, you see that absolutely nothing of the sort happens. So with the exception, so these are the 6 most popular non-generic detections in terms of the Sophos family label that we found in all of our months of data. So we've got Ramnet, iDrop, and Scribble across the top. And with the possible exception of Ramnet, you can see that the average, or the median distance, the 95th quantile of the distance, and the 99th quantile of the distance, these are almost dead flat for all families across all times. So each individual family of malware, their representation that the machine learning model is sort of learning how to classify these in this high-dimensional space, these are not changing significantly over time. Okay, so that was great, except that requires labeled data. I need to know that my Ramnet samples from February are indeed Ramnet samples and not something else. So how can we do this if we don't have any labels on our data? Well, we're going to cheat a little bit, and I have to pause to say that the next couple of slides are work in progress, so they're a little bit rough, but I still thought they were interesting and exciting enough to share with you guys. So we're going to look just at distances, not between families, because we don't know what family the new points are assigned to, but just the closest training point in any of the training data. And then we'll throw some model confidence in on top of that just to sort of have a nice 2D plot. And the nice thing about this is you don't need any labels. You just need to be able to run the sample through the model and compute the confidence, and then measure the distance between that sample and your training data. And what you end up with is a slightly confusing plot that looks like this. So the x-axis here is going to be the confidence. 0 is totally different from the existing training data. 1 is totally similar to the existing training data. The y-axis is the distance. The higher up you get, the further away from the training data each of these individual points were. And these lines, think of them as sort of a topographical map showing you where the January data lives in the same representation. So each point in this, again, is a single PE file. This is from the July data. And if you just eyeball it, you can kind of see some clusters that pop out of it. And indeed, if you drill into those and you sort of select those clusters out and you go and you check the family labels, which we've got because this is from July 2017, you can actually see that a bunch of them are either new generic detections, new clusters of generic detections, or families in the July data that did not appear in the January data. So they actually are new families that this model has been able to pick out through this representation. I also, full disclosure, you also get a bunch of benign ones that are in there as well. But we're looking at ways to sort of try and filter that down and get it to work a bit smoother so there's not as much sort of picking and choosing that has to go on. Okay, so to wrap up, I hope I've at least given you a flavor for the sort of research that we're doing right now. And if you take nothing else from this, I want you to take away the message that machine learning models decay in interesting and potentially useful ways. So you can use them as analytic tools and not just simple, this is malware, this is benign-ware, this is malware, this is benign-ware. The two techniques that we exploited for this were confidence measures and distance metrics. There was much more detail in the white paper if you're interested. And I want to leave you with a couple of sort of practical takeaways. So first off, machine learning and old school sort of signature-based malware detection, these are complementary technologies, right? They play very well together and they make up for each other's deficiencies in a very interesting way. The rate of change of existing malware, at least from the perspective of these ML models, is actually really slow. Existing families do not seem to change substantially over time. And this is sort of supplemented by the turnover rates that we saw in the holistic view, where the rate of decay of the machine learning model is driven much more by old samples that simply are taken out of production, aged out, or are just detected so well that nobody bothers to pass them on anymore. And again, so we've got some estimates for rates for how these things change over time. The turnover rates, these are going to be data set dependent. There's also some error bars around them, but at least the relative rates I hope would be relatively stable. Okay, and that's it. I just want to sort of thank all of the usual suspects, in particular Richard Cohen from Sophos Labs, who helped correct a few of my more egregious errors discussing malware, Josh Sachs and the rest of the Sophos data science team, Black Hat staff and support, and all of the woodcuts from the Alice in Wonderland were done by John Tenniel. We have code and tools coming soon. We're still trying to work out some internal issues with approvals, but there will be at that GitHub link. I've also updated the slides, so if you grab our slides, you'll have that link in there. And with that, I think I have enough time left for a couple of questions, so thank you very much.
Hi, thank you for the presentation. Two quick questions. First, did you try looking at, it was kind of obvious that this was done mainly on PE files. Did you try looking at files which are not PEs as well and do the same kind of, to observe the decay and confidence issues in the same way? And also, do you think it would be useful to also generalize this not to just a specific family, but to specific types of threats, let's say ransomware in general, or keyloggers in general, etc.?
So the first question was, have we tried this on other kinds of malicious artifacts? So we have tools that we're looking at internally to look at other malicious artifacts. We haven't actually tried these techniques against them. That's definitely on our radar, though, and we're hoping it'll turn up a lot of the same results. As far as the second question, do we want to look at, instead of individual families, maybe more broad classifications of malware? Yeah, I think that's a really good idea. I hadn't actually thought about that, and sort of isolating which families belong in which class at a higher level is maybe a bit of a technical challenge, but I agree it would definitely be very interesting to look at.
One more if you got time. Have you guys looked at distance between families as a way of measuring code reuse between them?
So we haven't explicitly dug in to examine code reuse because we're generally dealing with binary artifacts, and a lot of those actually end up being packed or encrypted. So that significantly increases the difficulty of it. Again, I think it's a really good idea. It's just something we're a little under-resourced to take on, I think.
Can you give some details on the distance metric that you're using? Like, are you looking at the KL divergence of the logits, or are you looking at something more, I guess, like a hash or something?
Yeah, the distance metric we used was just L2 distance within the feature space.
Okay. Thank you.
Hello. Hey, question here. Sorry. As you know, the distance, how generalized the model is depends on how you select the features. I guess in your model right now, you're using a fixed set of features. Mm-hmm. Have you thought about, make the features more general such that when you see new samples, you can still using the same set of feature, but what I'm saying, the novel samples may not look as novel as you presented here. So how do you evaluate the features you have, to make the features more general so the new samples may not look that novel?
So how can we, is the question, how can we maybe,
Yeah, I guess here in your
If we see-
models, you use a fixed set of features, right? Which, does not change along the way. But have you, when you build the models, do you evolve the features as well? Like I extract more features such that, new samples may not look that novel anymore, right? They still stay closer.
so because we're using a feed-forward neural network, that does drive us to a fixed set of features. So as a separate research project, we are always looking at what are good potential changes that we could make to our features that maybe might help us organize better or classify better as new samples enter our distribution. But yeah, this was all done with a fixed set of features. I know there's some other techniques that use like convolutional or recurrent neural networks to sort of maybe be a little more adaptive, but we didn't look at that in this talk.
Thank you.
And I think that is about it. So thank you once again.